start now. Right. So, in the previous class, we were looking at graph neural networks, and before that, we had looked at neural network research. But in general, up to this point, we have been looking at models that primarily function as classifiers, some sort of classification, some sort of predictions. Another very popular usage of any sort of deep learning model is generating new data given say some existing data. And the data is not necessarily the same as whatever you have seen maybe during training, but something new and something more creative than the original data than on which your models have been trained. And this is a very interesting use case and extension. I mean, there are a lot of extensions to these use cases. And as a result, you have a lot of things, including say your chat GPT and other things, which are also in a way these are also generative models. You also have image-based models and others. So we'll look at the core philosophy behind these sort of generative models, and also we'll start looking at a few architectures for generative modeling of say primarily images. We'll see at this point. Maybe we can move to text as we move forward. Okay. So right, the objective of any sort of a generative network is to generate realistic data. I mean, using some sort of an algorithm. And obvious example is to generate maybe natural images of people doing something. You write text, and the model basically shows you a corresponding image that is exactly according to the description that you wrote for that particular image. You can also maybe generate natural audio. You can record your own voice and maybe take a song that the song is sung by some other artist and basically map your voice to sing the same song using the same, say, tonality or something like that. You can generate text, you can generate video, because obviously you can generate images. Video is nothing but a sequence of images showing an action, some event. So all of these things are something which generative models would want to do. Obviously, generally you try to use separate models, but there can be multi-model models. They can handle maybe multiple types of these modalities together as well. Okay. So will right. I mean, generative models will try to generate realistic data by learning from real data. So in all of these processes, if you want to generate something, you should have access to the real world data for that particular domain, so that you can then generate samples for those that particular domain. Okay. So, for example, if you have images of bedrooms, you have nice, well furnished, well lit, and well colored and designed bedrooms, you can train a model on top of it and then be able to generate any number of bedrooms that may look even better than the original set of images that you trained it on. Right? Now, when you're trying to generate any type of data, or maybe when you're trying to learn to generate any type of data, the assumption is always that whatever data you're trying to replicate or generate from, that data itself has been generated from some underlying unseen probability distribution. Just like say um, you have say a number that has been generated from say a Gaussian distribution. Similarly, we can assume that any image is also generated from some underlying distribution. Okay, which obviously would be a very high dimensional complex distribution, considering say if you're taking an image, a large image, and it has so many pixels, and these pixels are not necessarily independent of each other. They're somewhere dependent on each other as well, so that it gets to represent a proper structure within that image. So if you can consider that entire image a 2D vector, if you're considering only one channel, as um, as a very large vector that has been sampled from a particular distribution. If you can know that particular distribution, I can identify the properties of that distribution. You can then generate more samples from that distribution. Just like if I tell you that this particular data has been generated from Gaussian distribution, you already know the form of Gaussian distribution. If I tell you the properties of the distribution, you can generate more samples from there. So generative model generally follows the setup of getting to know either directly or indirectly. I mean, you'll not be able to exactly get the actual distribution, but you're trying to approximate the distribution from which your given data has been generated. And then from that approximated distribution, you try to generate more samples, which turns out to be very good, in fact. And we'll see some of these cases. So, for example, the number 0.25 can be generated from a Gaussian distribution, which has maybe a mean, zero, and standard deviation. It's a standard normal distribution. So now, if I tell you that this number has been generated from this particular distribution, I can generate any number of samples from this particular Gaussian distribution. That's the idea behind generative networks. However, the whole point behind this setup is that you don't know the underlying distribution; it's unknown. And especially if you're considering a very complex data, like say an image or say an audio sample, or in fact say a video or text, these are not very simple distributions. Because they have a lot of moving components. They have a lot. You have either for images, you have a lot of pixels, and each of these pixels are related to each other somehow. So the underlying distribution itself is going to be extremely complicated. And ideally, you will not know the distribution of the data from which this data has been generated unless until you have created that data from explicitly using some distribution. You will not know otherwise. So we have to find out a way to approximate this particular system. What we have on the other hand is lots of samples from the distribution. So consider, say, your any sort of image data set. Say, for example, if you have the MNIST data set, which basically are images which contain images of handwritten digits. So you have a lot of images. So given samples of this distribution, we can estimate some of the properties of the distribution. And based on that, we may be able to sample from the distribution too. So a simple example can be that suppose if I give you, say 500 samples, 500 numbers between certain range. And I tell you that these have been sampled from the same distribution. So I'll try to fit a distribution on top of it. And the easiest distribution, or the most, distribution that you will usually find in natural things is your normal distribution, or your Gaussian distribution. So what I can do is that I can estimate the properties of a Gaussian distribution and replace this particular, identify and find out a Gaussian distribution that basically supports this set of samples. So what I'll do, I'll maybe find out the mean of all the samples. That gives me the mean of your distribution. If you remember, the Gaussian distribution has the defining properties are the mean and the variance, or standard deviation, whichever you want to work with. So you'll have a mean, or say a standard deviation. So if I give you these 500 samples, I'll try to fit, say, a Gaussian distribution on top of it, and I will try to find the mean of the samples. That will give me approximately the mean of the Gaussian distribution, which is supposedly the parent distribution of the samples, and then I'll find out the standard deviation, both of which are very easy to calculate if I give you the samples. And once I have these, I can now sample even more samples. I can sample any number. I can generate thousands samples from this particular distribution. And roughly, since these 500 samples have given me the properties of the parent distribution, so the new samples that I generate will also follow these approximate distribution and will be similar to how these 500 samples are. So that's the general idea of what we'll try to apply even to generative models. Say specifically for images, we have access to a lot of images, and based on these images, we'll try to learn an underlying distribution. And once you have learned that distribution, we'll try to sample from that particular distribution to generate more and more images. Okay. Yeah, and it's exactly what's mentioned over here. Right. So before you can move any further into your generative modeling, let's look at one term that we had seen much earlier at the beginning of the second fractal, which was basically the concept of an autoencoder. By the way, I'm maintaining the the lecture series. I'm keeping it as fractal 2 and lecture number, so that there is no confusion as such. Even though I think we have passed fractal 2, we are basically into fractal 3 now. But I'll still be continuing with the same at least naming convention, so that there is no confusion about the lecture numbers from my portion. Okay. So for your autoencoder, we had basically discussed initially what an autoencoder basically does. So it's a network which will have an encoder subnetwork and a decoder subnetwork, and its objective is basically to find a very good compressed version of the input, which can retain as much as the important features of your input and maybe discard out the unimportant features. Okay. So the main goal of any autoencoder is basically to achieve a good compression. And how does it do that? It basically ensures that you can reconstruct your original X from the encoded or compressed version. If you can do that, which means that you are ensuring that all the relevant information is still preserved in the compressed version, and you have not lost out on any of the important information. As a result, you are still able to get back the original uncompressed image or uncompressed data. That's the basic concept behind any autoencoder. Okay. So if you look at these two portions separately, it has an encoder portion that gives some embedding or some good representation of your actual say data, and you have a decoder portion that takes this particular representation and produces an image. So it produces an image. What can we do to ensure that it produces a new image maybe from the same distribution? That's the whole idea that we'll cover in this particular class. Right. So the encoder function converts the input data into a different representation. Generally, it's a much more compressed representation, and a decoder function or decoder network that will convert back the new representation into the original data. And while training, as I mentioned, the objective is to preserve as much as information as possible, and this is achieved by enforcing that the output that you get after decoding the given compressed version is the same as the whatever was the input to your input. As a result, you're retaining as much as important information as possible. Okay, and we had seen different types of. I mean, we had discussed the denoising autoencoder as well. So we can use different types of autoencoder to additionally maybe support even more types of objectives. Like say for a denoising autoencoder, it's used to basically remove noise from any given say input image. So if you add while training, what you do is that you take an image and add some random noise to it, and um, I mean, while finding out the loss, you'll try to reconstruct the actual image without the noise. So that way, you're trying to learn to denoise your images. So then, once this is trained, you can then use this particular network to denoise any noisy image that you get from some not so good source. So that way, you can have a lot of types of different autoencoders for solving different types of problems. Okay. I think we had also seen back then an example of an autoencoder, which was basically, if we have not seen, then we'll show it. I will discuss that today. So generally, our first intuition, initially, will be to use, say, fully connected networks because it's easier to generate create an architecture using a fully connected network because we'll not have to think about the intermediate feature size and everything. So your fully connected autoencoder can work very well in compressing your given, say, input and coming up with a good feature representation that is a compressed version of your input. Okay. However, not all types of data will be well serviced using, say, only fully connected layers. So you can also look at something known as convolution layers. I think this was covered in your first fractal as well, how convolution layers are good for data where the spatial relationships are important. For example, you have high dimensional data like images where you don't just linearize the entire, you cannot just linearize your entire image and expect that your output will be good. Because say for any fully connected network, if you want to send an image to this particular fully connected layer, you'll have to linearize the entire say image. So if you have an image of size 28 cross 28, you'll have to basically create one single vector of which is of size 28 into 28 and cross one. So and then only you can pass it to a fully connected layer. But as a result, you will be destroying a lot of spatial information, which is not advisable. It might still work for very simple data sets like say MNIST, where there's not much complexities as such in the data itself, but for a larger and more complicated data, you're not expected to perform that well if you're only using say, a simple fully connected layer for your entire. So we'll try to compare the performances of both your convolutional autoencoder and your fully connected autoencoder. There's nothing different as such for your convolutional autoencoder, just that since you're using convolutional layers, you will have to deal with the encoding portions and decoding portions in a slightly different manner. You'll have to reduce the size as usual so that you get a compressed version of that image. The compressed version may be a single vector or it may be a convolution output feature. So it may be output of a convolution layer, which will again contain a set of features, channels with some two-dimensional size. Right, and we'll see how autoencoder using convolution layer will perform maybe better in many cases as compared to say a fully connected layer based auto encoding. Now, before that, in your convolution layers based autoencoder, you'll have to downscale the images. Downscaling the input was easier for a fully connected layer because you simply had to, I mean, if you had your input of size, say 784, you could simply create a fully connected layer that converts it to, say, size 256 and then maybe, say, to size 64 for your encoder, which would be output for your encoder, and then for your decoder, you could simply convert your 64 back to 256 and back to 784, which is your original image size. So it is comparatively easier when you're doing, I mean, using a fully connected network. But with a convolution layer, it will be slightly tricky because now you have to downscale the images, not using I mean, using say convolution filters, which are generally much smaller than your actual image. So you'll have say filters of say size 3x3, and using this, you may have to maybe achieve some sort of a downscale. So there are many ways of performing downscaling. The most popular ones are the first approach is using pooling. So what you do is that your convolution layers will simply process your image. And if you remember the operation involved in convolution layers, if I give you any, say, image of a particular size, say W cross H, I mean, at least ignoring the number of channels, you can, if you apply a 3x3 filter, you will get something like this. Say, one, two, this one, right, I think yeah, you will get something as the output will be something like this. So if I use a padding of 2, okay, wait, right, so let's try it. If I use a padding of say sorry 1, and I basically try to find out the output size of this particular weight, I'll be left with 3 minus 2 minus 3 plus 2 plus 1, which is I'll get back here original width itself. So in many cases, you will see you will be using say convolution layers of size 3x3, padding 1, stride 1, and this particular type of convolution layer will not change the size of the basically the input channels, and however the decrease in size will be achieved using something known as a pooling layer, which I think you may have also covered earlier. The pooling layer will, I mean, it also has a filter, and it also functions similar to, say, in terms of, say, sliding across your entire input, similar to a convolution filter. But what it will basically end up doing is it will perform an operation like max pool, min pool, or average pool. So if you have an image and you have applying some pooling, say of size 2 cross 2, it will take regions of 2 cross 2 and replace this entire cell using the average or the minimum value or the maximum value of the cell. So if the maximum value is 1, so you'll replace that point by 1, and then it will slide one step to the next. So that way you're achieving some sort of a decrease in size of your individual channels while retaining the most useful information. So if either you're maintaining the maximum number or the minimum number or the average number, and that way you're trying to reduce the size of your input filters. So you can achieve this sort of a downscaling of your image. So you can see there will be a downscaling, obviously, because if you have an initial image of size 10 cross 10, now for every 2 cross 2 regions, you are replacing the 2 cross 2 region by a single value. So obviously your image size will also decrease at every level. So you can either downscale using pooling, or you can use a simple convolutional layer only with a stride that is greater than 1. So if you use a stride that is 2, the width size will obviously, generally it will be close to half. So that way you can reduce the size. And why are we reducing the size? We want to reduce the complexity or the storage space of any of your input image and bring it to a lower dimensional space, and then get back the original input by maybe going the reverse direction. So we'll also see how to do upsampling or upscale. Okay. Similar to what a convolution, what a fully connected autoencoder was doing. Okay. Right. So it's something like this. You have a pooling operation that basically with say some filter and some padding and all, and it basically starts mapping you to a lower dimensional space where the output in this particular case is only single. Right. Now, the other operation is once you have basically kept downsampled to some level and you now have your compressed version or your downsampled version, says it. Now you have to upsample it, similar to your standard fully connected autoencoder as well. Now, in your autoencoder, again, this was fully connected autoencoder. Again, this process was relatively simple. You simply added a few layers, which was exactly equal to. So, if you had reduced from 784 to 256 to say 64, you would now do just the reverse. You'll create another FC layer which moves 64 and takes into INSPO and produces 256, and another that takes 256 size and produces a vector of size 784. So it's easier in say your autoencoder. You based on fully connected layers, but for convolutional layers, you'll have to use something different. You'll have to use something known as a transposed convolutional layers. So you don't have to worry as such about this particular setup because transposed convolutions are provided by all the frameworks that we have, including say PyTorch, etc. But the idea behind transposed convolution layer is that you give me a particular say input. I take one cell and I will retrace back the original output, that original input that actually gave you this particular set. So if your original convolution had converted this 5x5 image to this 2x2 2x2 feature, deconvolution will basically take you back. Obviously, exactly transforming back is a very difficult task because you don't. There will be a lot of moving parts. You have learnable parameters that has gone into your convolution operation. So generally, what transpose convolution will do, it will try to learn a filter that gives you back a higher sized feature, and because you're training your autoencoder to basically reproduce the same image, this will ensure that these upsampled images are corresponding to the original, say, original set of features that you extracted. Okay. At least indirectly, that will ensure that, so that you're retaining as much of information as possible. Okay. And that's the idea behind your transpose convolution. Your convolution basically takes a filter, and then you're based on your filter, it applies the filter and gets back, say, one specific region from this particular 3x3 region. Transpose convolution, on the other hand, will take this region, will use this particular filter, and it will give you a particular region that looks like this. So it's just the reverse operation, and that way you are trying to get back the same size, just like what we did in, say, your fully connected network-based your autoencoder. So it's this particular operation is primarily used for upsampling feature maps in neural networks, specifically say some autoencoder-based structures. Okay, now we'll look at one example and then discuss the merits and demerits of, or at least compare the different approaches to building your autoencoder. So I'll just shift once to a different screen. Yeah. Okay. So if you look at it, this is standard setup. For it's a PyTorch based code, so you can load your. We have basically loaded the fashion MNIST data in this particular setup. Okay, and we have built a standard fully connected layer based autoencoder. In this particular setup, you can see a set of linear layers of fully connected layers, which is there over here, and based on these setups, you can see that the size of the intermediate features will go down till the end of the encoder, and then the decoder basically reverses this process and gets back the original image. In this case, the original image is of size 28 plus 28. Your MNIST images, the fashion MNIST images, but they're still 28 plus 28. And the operation is basically in the forward pass, you will encode the given image, and then you will decode the encoded values or encoded or compressed representation to get back the original representation. And ideally, initially, you'll not get the original representation, but through training, you'll try to achieve that whatever is the input X, you get the same as in the output. Okay, let's come to the convolutional autoencoder, which will be, as mentioned, it will be trickier as compared to, say, your standard encoder, fully connected autoencoder, because now you have to use convolutional layers. So in this particular setup, you can see that we are using max pools to basically reduce the size of the input. And the convolution layers are also there, but they are not necessarily reducing the size of the input, because if you look at here, the stride is 1 and padding is 1. So if you have any convolution layer which is a 3 cross 3 convolution, which is using 3 cross 3 convolution, stride 1, padding 1, that particular setup uh, will not change the size of your, basically, let me again write this here. This particular setup will not change the size of your given input, stride 1 and padding 1 and 3 cross 3. Here, the reduction in size is achieved using your max pool operations over here and here. And you can see how the size of the images are changing. So initially you had 1 cross 28 cross 28, which is the size of your standard MNIST layer, MNIST data, or fashion MNIST data in this case. And fashion MNIST only has a single channel. You have black and white images. And the first convolution layer basically only changes the number of channels and doesn't change size. And then you have a max pool layer which simply halves the size of the feature map. So you're 28 plus 28, now you have 14 plus 14. Again, the next convolution layer simply does not change the number of the size of the feature maps, but just the number of channels. And then finally you have another max pool layer which again halves basically the size of the feature maps, and this will be the size of your representation, intermediate representation or compressed representation. So initially you had an image. It's not large, but it had an image which had 28 plus 28 pixels, and now you have something of the size 8 plus 7 plus 7. You can reduce it further too. There's no hard and fast rule that you have to reduce it to only a particular size. Now we'll simply look at the decoder. Decoder will take this particular 8 plus 7 plus 7 as an input. So you have 8 channels of size 7 plus 7, and will try to regain back the original size. So you have your transpose convolution layer, which again will try to get back the original at least at this stage you had 16 channels. So you'll try to get back 16 channels, and each channel of size 14 plus 14. And accordingly, the kernel and the stride has been chosen. You can play around with these parameters to find out what will be the output size at every level. And you have another convolution layer which then takes this 14 plus 14 to 28 plus 28, and the number of channels is reduced from 16 to 1, which is the size of your actual input, 1 plus 28 plus 20. And once you do that, you are basically, at least in terms of auto encoding, you have done the entire process. Now what is left is to train this particular model. So this forward function is basically performing the encoding step first and then performing the decoding step, which is again similar to what we had seen in your fully connected based autoencoder. What I've done over here is basically train both of them parallelly, and training them only for a single epoch. And I'll show you the difference as well as the strength of autoencoders after training only for a single epoch on this particular data set. Okay. And this is the result after a single epoch. And if you look at it, this was the set of original images. These are extremely low resolution images. These are 28 plus 28 images only. So as a result, I'll just clear the screen a bit. Yeah. So as a result, you will have these sort of pixelated images, but these are the original images. And after one epoch of training, this is what your fully connected network-based autoencoder is producing, and this is what convolution layer-based autoencoder is producing. And if you compare these, fully connected network-based autoencoder has performed well, no doubt, it has performed well. But just see the difference between what the fully connected network is producing and the convolution network is producing. The convolution network within a single epoch is much more detailed and much more closer to the original, say, image as compared to your fully connected network-based autoencoder. And you can see this across all the images. You consider this image, or say this image, and even this image. The convolution network-based autoencoder is much more detailed and much closer to the original image. Obviously, this is the result only after a single epoch. If you train for more number of epochs, maybe the fully connected networks will come close to the convolution layer's output. But this is considering that this is a very simple data set, which simply has black and white images of shapes that are well positioned, and the background there's no distraction and other things. Considering all of those factors, even within a single epoch, we can see the difference between, say, a convolution layer and a fully connected layer. So generally, when we'll try to work with images, we'll try to work with convolution layer-based autoencoders, because that will perform better in terms of performance, getting, say, a better representation of your images. because when you look at such reconstruct images, one thing that should come to your mind is maybe the intermediate representation that was generated by your fully connected layers was not good enough, or maybe lost a lot of information, as a result of which you're not able to regain the original image. Another reason that can possibly be there is that because you're losing out on the spatial information, while you're reconstructing that same image, you're again not able to properly reconstruct the spatial information of the individual pixel. As a result, it's not as detailed as, say, convolution layer based autoencode. Okay. Um, so we'll move back to our slides. Yeah. So this is what I was talking about. If we have a fully connected layer with autoencoder and a fully convolution-based autoencoder, within one epoch, you can see the difference between the type of reconstructions it is producing, especially evident in this particular set. Okay. Now, so again, generative models. So we were discussing generative models before moving into autoencoder. So finally, we want a generative model. So how do you use an autoencoder to become a generative model, or is autoencoder a generative model uh, in itself, which we can then utilize and get maybe new images? So generative models will try to learn the probability distribution of the data itself, as I mentioned earlier, so that you can then sample new data from these particular distribution that you have learned. Okay. However, autoencoders are not in this business. Their specific purpose is to compress the input image, learn a compressed representation of the input data, which does not lose out on too much of the valuable information that are present in the actual image or the actual input. Okay. So it's typically a deterministic mapping. So it's a one-to-one mapping. You map that image back onto itself. Okay, and you do not try to learn any sort of underlying distribution that a set of images maybe have for in that particular data. Rather, we are only concerned about, in fact, overfitting your given autoencoder to exactly produce the reconstructed version, which is same as your original input version. Input data. So your autoencoder decoder pathway, or the encoder decoder pathway, by default will not capture or generate samples from some probabilistic distribution. Therefore, it will limit its ability to create a novel data points or novel images. Okay, and once the autoencoder has been trained, we'll have both an encoder as well as a decoder, but there will still not be any way to produce any new content, because this whole network depends on an image given to it, maybe image given next to it, and then producing back the same image. So if you're always producing back the image that you got as an input, how do you then generate new set of images? Okay, and there can be one way to approach this particular problem, but we'll see that that way also will not be very effective in an auto input. So generally, a simple naive autoencoder will not be considered as a generative model, because by default it has no such features or properties that you can use to generate new images or say new kind of data or generate new type of data. Okay. Now, we might be thinking that we already have an encoder that can encode any particular image into a given, say, compressed version, and we have a decoder that takes that compressed data and produces the image back. So why don't we basically change that encoded version? Suppose we have this encoder E that took an image X and produced encoded version of that image Z, and the decoder basically decodes this and gets you back the original image. So what ideally, if once these encoder and decoders are trained, ideally the decoder has learned to map this particular vector representation to an image. So why can't we simply modify this set, and in that way sample randomly from this latent space, okay, and decode it to get a new image? We should be able to do that, because at the end decoder knows to translate a given vector into an image. So let's try this particular setup. We'll try to achieve this by using a very small magnitude noise vector to your original z. So now you have, instead of z, you have z plus n, and you will pass this new modified, say, new encoded vector to your d. and we'll see what kind of images we are getting, and whether we can get something which is useful for us. Turns out, if you do that, you will actually not get back a very good image. And in fact, what you will get back is a noisy version of the same image itself. Okay. You're not getting a different image, you're simply getting back the same image with some additional noise. And why is this happening? Because we have basically overfitted our network to work to reproduce the actual image. So it's always trying to reproduce the actual image. So even if you add some noise, maybe the output is still noisy, because in this particular case, you're not doing any sort of denoising autoencoder. But then the output will again be somewhat similar to the original input itself, without creating any sort of a radically new image as such. So we can be sure that if you are depending only on your naive autoencoder to generate new images, that endeavor will not be very successful. We need to look into something else to make your autoencoders able to generate new images from a particular, say, domain or a particular, say, distribution. Okay, which is where the concept of a variational autoencoder comes into play. Remember, we had seen and we had, identified this term much earlier in this particular set of lectures when we were discussing something about zero shot learning, where we had something known as VAE. And at that point of time, I had simply mentioned that consider a VAE as a special form of an autoencoder. So, which is actually what an variational autoencoder actually is. It is still an autoencoder which has an encoder as well as a decoder, but something else will go on in the middle, which will help you to basically generate new samples, okay, which are actually maybe which will cover actually a lot of different types of images, for example, and can be then considered as a proper generative model without, even though it's a autoencoder. So we'll see what this model actually does and how it behaves and what kind of properties it has. So in an autoencoder, the information from the input data is mapped onto a fixed latent representation or some compressed feature. At least the encoder does that particular work. Okay, and that will be useful if you have some sort of a deterministic predictions to make. So remember that we had used an autoencoder to actually train a neural network layer-wise in an unsupervised manner to then create an entire network, and finally we had some FC layer to train the network on. You can also use an autoencoder, a simple autoencoder, not a variational autoencoder, to basically learn embeddings for images, good embeddings for images. And then what you can do is you can discard the decoder and simply learn a fully connected layer on top of this particular encoded representation, which is also a good thing because you have learned the structure or the code important patterns within your data, which is contained within your compressed version. And on top of that compressed version, you're learning a fully connected layer. So if you have some sort of a deterministic problem where the encoded information explicitly corresponds to the given input data, then your autoencoder will be fine. But if you have a generative network, if you want to build a generative network, autoencoder in itself will not be good enough to give you good generations. Okay, which is where your variational autoencoder comes into play. So variational autoencoder basically converts your input data to a variational representation vector. So again, look at the terms that we are using. It's again some encoded version of that vector. Okay, but we'll see how we arrive at this vector. This will be something different which will happen over here. Okay, this particular vector will be different from your autoencoder because it will have some elements. Specifically, it will have two elements, which will make it useful for us because then we can model a distribution around this particular. We can model this particular thing as a distribution, and then we can sample from this distribution to generate new images. So we'll see what that is. Okay. So this sort of a probabilistic property, we'll see how it is probabilistic and all. Will make it a generative model because if I can ensure that this encoded version is from some unknown probability distribution, then I can directly sample vectors from this distribution and pass it on to your decoder, and your decoder can generate images from this particular distribution. Okay, we'll see how to achieve that. Okay, so the latent representation in your VA will composed of two things, as I mentioned. One will be the mu vector, another will be the standard deviation or variance, whichever you want to use. I think you can have different versions of the same thing. But why are these two things important? These are two things which, if you use, you can define a Gaussian distribution based on them. Okay, if you have the mean and the standard deviation, and for say that is for a univariate case. If you have multiple dimensions, we'll have a multivariate Gaussian. But again, a mean and say in that case a standard deviation or a variance, or in multivariate case a covariance, will allow you to define a probability distribution, Gaussian probability distribution, and based on that you can then sample new intermediate these compressed representation, which you can then pass it on to your decoder to produce new set of images. Okay, so autoencoder is VAE is basically an autoencoder where the encoded data is, first of all, it has two parts, mu and a sigma, or say standard deviation and mean, or variation and mean, which is then regularized during the training period in order to ensure that the latent space has good properties, allowing us to generate data. So, I mean, you have your input, you have your encoder that will generate two vectors, and we'll use these two vectors to sample, say, a particular distribution, say, by a particular value, say z, and using that z, the decoder will give me back the x. Okay. So this is generally how your variation autoencoder will work. But we have to ensure that this mu and sigma are actually close to some mu and sigma of a Gaussian distribution. Okay, so that we can then assume at the end, when this particular training is done, that if I sample from that same Gaussian distribution, I can then generate any number of images from there. So for that, to achieve that, we'll have to do some sort of a regularization operation at this stage as well. So remember, in your standard autoencoder, you just had one single loss, and that loss was basically your the difference between your actual image and the reconstructed image. In this case, we will have two losses, which we'll see. One loss will be the same reconstruction loss, and the other will be this regularization loss. Which will try to map these mu and sigma vectors that you get in the middle. We'll try to map it to some Gaussian distribution, and if we can do that, we can then sample as many number of these intermediate features as many required from that Gaussian distribution and generate as many sample images as possible. Okay, right? And this particular VAE was proposed by Kingma in the year 2013. It's a very famous paper. It has, I think, over 3,000 or so citations on, and it's very interesting paper. And it's one of the initial works that basically introduced the concept of your deep learning based generative model. Okay, this is what your VAE will generally look like. You will have an input. Okay, I think we have not shown the full encoder over here, but there will be a full encoder which will generate your mean and standard deviation, and we'll discuss all of these in the later slides. From there, we can sample a latent vector or say an embedding for a given input image, and that input image I'll basically send it to your decoder, which generates your the image that is supposed to be the same as the original image. Right? At least this portion is still the same. Your reconstruction has to match the original part, which is that loss is still the same. What will differ is your intermediate representation will now have two components, and you also have a sampling step, and you'll also add some sort of a loss so that this particular portion is close to some Gaussian distribution. Right. So again, as I mentioned, it will have both an encoder as well as a decoder, like a standard autoencoder, except that you will have some difference over here at this particular stage. Okay. And again, this is trained to minimize the reconstruction error between the original data and the reconstructed data. Okay, and we'll also do some sort of a regularization on top of these, say, mu and sigma that you get, a mean and variance that you get. Right. And the objective, and finally, will be that initially in an autoencoder, you were encoding that input as a single vector, which was representing some point in some lower dimensional space. Now we'll encode any given input as a distribution in that latent space. So if you're encoding an input, you get mu and sigma, and that mu and sigma can be mapped to some Gaussian distribution. So that entire distribution itself will correspond to that particular image. And what we'll try to do over time is that we'll try to map all images to a common set distribution. And if you can do that, that means if all images are coming from a particular common distribution, that means you have identified at least approximately the parent distribution that which generated all of these images. And then therefore you can then sample from that particular distribution and get new and new images.
Sir, one thing I want to ask here.
Yes. Yes.
So this concept is coming from generative learning, right? If I'm not mistaken.
Yeah.
In first fractal of machine learning, we studied something as generative learning, where we were identifying the samples with generating the given, data sets. I'm predicting the samples, and based on that, we will calculate the likelihood and get the best samples out of it. Correct.
Okay.
The other part is, sir, are we always going to do use away with the generative learning? Using the Gaussian distribution only?
Yeah. So see, ideally we don't know the distribution. So we'll try to approximate that with the one distribution that is the most common distribution that is available everywhere. I mean, most of the natural items, if you try to find a distribution, you will find that it's distributed using Gaussian distribution. So since we don't know the distribution, we'll try to map it to a Gaussian distribution. We can also map it to other distributions as well, depending on your requirement. But generally, we try to map it to a Gaussian distribution. It's also easier to sample from a Gaussian distribution that way, and easier to also model a distribution, Gaussian distribution, because we only require the mu and the sigma for that.
Okay.
Okay, right. So, right. So the way model will be trained as follows. You will first have the input that will be encoded as a distribution, basically as the mu and sigma. And then you will sample a particular value from this particular distribution, and that will be my encoded value. And that sample format will be then sent to your decoder, and we can compute the reconstruction loss. And on top of that, we can also have a regularization loss, which ensures that this particular mu and sigma are actually corresponding to a Gaussian distribution. Okay. And finally, we backpropagate this particular loss so that all the layers get trained. Your encoder and decoder both are getting trained. I mean, in terms of decoder training, there's nothing much difference, at least at this stage. But the encoder gets to train on both your reconstruction loss as well as your regularization loss. And we'll see how to we'll simplify and see how to do the regularization process. So that's how your autoencoders and variation autoencoders are different. Autoencoders would have given you a simple latent representation, a single vector Z, which was then passed on to your decoder to get your reconstruction. In this particular case, you will be getting some sort of a distribution rather, and then you're sampling from the distribution and passing that sample to your decoder. But this sampling process is going to introduce a big problem for us, and we'll see how to deal with this particular set. Okay. Right. So, in practice, we, as mentioned earlier, will choose this encoded distribution to be a normal or a standard normal distribution or Gaussian distribution. Okay, so that we can train the encoder to produce mean and variance that lies within that particular distribution. If you can map multiple such images, all of such images within a common distribution, then what you're basically ensuring is that since our hypothesis is that all of these images have come from some parent unseen distribution, we are mapping all of them to a common distribution, and now that distribution becomes our approximated parent distribution, which we can then use to sample new images. Right? So we'll enforce these encoders to produce something close to a standard normal distribution. And we'll see basically what we'll try to do is that we'll try to ensure that the mean is close to 0 and the variance is or the standard deviation is close to 1. Okay, this will ensure that all of these images are coming from standard normal distribution. And once we ensure that we already can sample from such normal distribution, we can simply sample new values from this particular distribution and pass it on to the decoder, and we can get images from it. Okay. Right. So the loss function, as I mentioned earlier, will be composed of your reconstruction term, which is the main objective for, say, at least from an autoencoder perspective. You will try to get back the same image, and you'll have a regularization term, which basically achieves this. It tries to bring your mu and sigma to the mu and sigma of a standard normal distribution, which has mu 0 and a sigma of 1. And this particular thing will be achieved using KL divergence. Remember, we had seen KL divergence while looking at your transfer learning or say distillation, where the objective was that we tried to reduce the difference between the probability distribution of the teacher and the student. So KL divergence will give you a way to basically compare two distributions. So in this case also we'll have two distributions. One is standard normal distribution with mu 0 and mu 1, and the other one will be whatever your encoder has produced in terms of mu and sigma. Okay, we'll try to bring this using KL divergence, and this will be the overall architecture of your VAE and the loss. So you can look at this loss. This is, you can also use much more complicated versions of your deconstruction loss, but this is a standard L2 loss where you're taking some input, you're getting some output, and you're basically subtracting them and taking the L2 loss from there. And you will have a KL divergence term which basically maps whatever mu and sigma you got to a distribution which has zero mean and identity, or say 1 as your standard deviation. You can see this is shown as an I because all of these cases you will not get a single value over here. I mean, your mean will be a vector itself. Sigma also will be a vector. So you're not getting a standard, say, simple univariate Gaussian, but you will get a multivariate Gaussian. And multivariate Gaussian is nothing but it has, you consider, say, multiple dimensions. Each dimension is its own Gaussian distribution. So you will try to reduce these two losses together, and through this process, you will get an encoder that basically encodes any given image into a distribution that is close to a standard normal distribution. And then a decoder takes samples from this distribution and produces something. Okay. Now, the problem that will come up because of this sampling process, we'll look into that. So it will be the sampling process. So given, say, some mu and sigma that my encoder has produced, I'll have to sample the Z from there, and only then I can pass it on to your decoder. So I can do something. We can directly sample from this distribution. How we can do that? Simply take an example of say PyTorch, where you can basically create a distribution using the given mean and standard deviation that this particular encoder produced, and then you can simply sample from the distribution. Okay, and then pass this sample on to the decoder. However, there will be a very major problem because of this particular thing. This particular step will detach because see, whenever you're training this particular model, up to this point, all of the you can trace back any point to your initial input, whatever input you got, and you have intermediate layers that are basically differentiable and trainable. And suddenly at this step, you are trying to use a sampling process. Sampling process will not be differentiable, because what do you differentiate in a sampling process? Sampling basically takes that distribution based on this mu and sigma and picks one sample randomly from that given distribution. So this particular step will not be differentiable. As a result, even if you're getting a sample and you're passing it on to your, say, your decoder to train the decoder, and a decoder produces some, say, reconstructed version of that image. Once you do backprop, the decoder is still getting trained based on the loss, but your backprop will get blocked at this particular step because you have lost that continuity in the middle. It's no longer differentiable. So encoder can't be trained anymore, which is a problem because you need to train both your encoder as well as decoder. So, I mean, we have to be very, we have to find a different way of performing this sampling while ensuring that this entire setup still remains differentiable and still the backprop is not blocked.
Sir, one thing. So while back propagating that at the where the samples are created,
Yes.
it's that we will get a very high value of error in the back propagation. That's why that won't be doable thing, because samples will be different, so it will not match. The error value will be very high. Correct?
No. Wait. See, what will happen is, sampling will be a totally detached process. See, first of all, sampling is not a deterministic process, right?
Okay.
See, it's not that you will sample randomly, you always get the same sample back. It's not the case, no. if something is not deterministic, how will you train on them? You're basically, what will happen is, up to this layer you're getting some specific output, and after this layer the output that you got, say Z, is not directly linked with either of these two values, either the mean or the variance. So there will be no combination as such. I mean, there will be a combination, but at least at this stage, there is no intermediate layer that performs this combination somehow. Or you're indirectly mapping this Z. You're not getting the Z directly from mu and sigma. So that's why they are detached. It's not because of the loss, but because you've broken. See, you're broken this deterministic conversion from one layer to the other. All of our conversions in every layer are deterministic. You have some weight and you have some input X, and you get the output based on this. You can also add some bias term. But suddenly after this layer, you have your X, which in this case are two values. You have mu and sigma, and then you're getting a Z, but there is no linkage between them as such. Okay, so that's the problem. There is no linkage is broken in between because of this sampling process. As a result, there is no deterministic transform between them. You cannot directly say I added mu and sigma, because that is not happening over here. We'll try to solve it and somewhere it in this way, but that is not exactly happening over here. So you cannot backprop. You're blocked over here. You don't know how Z was obtained from mu and sigma. That's the problem.
Okay.
I'll show you the solution, and then you will be able to appreciate this problem. Right. So the solution to this problem is something known as a reparameterization trick, which what it does is that it will take a sample from a standard normal distribution, okay, and we'll consider this as a constant value. And my Z will be obtained by simply taking my say my standard deviation, multiplying it with that constant value and adding the mean to it. So if you consider back my VAE and basically my problem that there was no deterministic way of finding Z from mu and sigma, now what I'm doing is I'm simply adding these two, but I'm also multiplying this term over here. And this term is some constant. Let's ignore that this is from some distribution. This term is some constant. So Z is basically H plus Z with some H plus Z with some number multiplied over here. Say sigma. As a result, what happens? Now this step is differentiable. Okay. Which was not possible earlier, because earlier what was happening is that you basically created a Gaussian distribution based on your mu and sigma, and then from there you sampled one vector, and that sampling is not a deterministic process, random process. Over here it's no longer random. This particular sample has been generated from this particular, say, distribution, which has 0 mean and standard deviation as 1, but it is acting as a constant over here. So when I try to find the gradient at this point, I can simply find a gradient very easily from here, because all of these have been created using this network. So all of these have multiple layers of values that has come to here and as well as over here. So I can still do differentiation and still move forward. Okay. One other interesting thing is, this is a standard way of converting any sample from a standard normal distribution to another distribution from which has mean, this has a mean and this has a variance. So let me show it freshly. So if you have a standard normal distribution which has mean 0 and standard deviation as 1, you can sample any value from here and shift it to another distribution which has mean mu and standard deviation sigma by simply doing this operation of. So this process has not come out of any random place. This process is basically taking a sample from a standard normal distribution and mapping it to a distribution with a given mean and a given variance. Okay. But what this is allowing us to do is, I am now giving you a deterministic way of converting your basically mu and sigma to your sample. As a result, this process is differentiable, and as a result, your backprop will not get blocked at this particular stage. And this is what is mentioned over here. So you have your mu and sigma, and you are sampling this particular value from a 0, 1 normal distribution, and then you're basically adding them in this particular. So weighted addition, and this is your new z. And over here, there is no backprop required because this is nothing trainable. We are simply sampling. You can consider a constant from here. The other thing is that even we are sampling a constant from this particular setup, this actually is a standard way of converting any sample from a 0, 1 distribution to a distribution which has mean G and say standard deviation H. And now we can continue with your regular process. You can simply send that sample to your decoder, and your decoder basically moves. Okay. So any doubts up to this point? We'll stop over here and maybe continue from. I will continue from here in the next class. Any doubts up to this point?
Sir, I didn't understand the point that how multiplying with a constant suddenly makes it deterministic. I mean, at
See,
this, the sampling
ignore
is random.
the constant for now. Ignore the constant for now. If you simply had mu and sigma over here, mu and sigma, and if I simply added mu and sigma to get my z and pass the z to your decoder, this will still be deterministic. Fine. And is this portion clear, please? If I simply add these two values and pass it on to my decoder, this is still deterministic. Okay.
So mu plus sigma will be both the unit. They will be vectors of different.
Same size. They have to be vectors of same size.
So in the encoder part, basically you are, making it the size is reduced to H and G value, right?
Yeah.
For to calculating mu and sigma. So each of these cells within H and G represent the mu and sigmas of the different feature sets which are coming from input, right?
You can consider that this, for example, now just ignore sigma, just consider mu. You can consider this to be an autoencoder that produces a reduced dimension of say size 3. Given an image of say size 7, it has produced a reduced compressed version of size 3. And you can consider this as another parallel process that produces another reduced version of size 3. Practically, this is exactly what is happening. The mu and sigma is something we are enforcing on top of it. Now what I'm doing is just ignore mu and sigma for now. Add these two values. This is a vector of size 3. This is a vector of size 3. In a way, you're adding the output of two autoencoders. Adding them, you're getting one value and passing it to a decoder. Two encoders and passing it to a decoder. So this process is still deterministic. There is no problem in backprop as such. What reparameterization trick does is does a weighted combination sort of. It adds some value, some constant over. Suppose I added 1 over here, or say 2 over here. That does not change when you perform. I mean, you can still perform any sort of. You can still differentiate this particular function. Right? If you want to find out dz with respect to du, you'll still get 2 if you have multiplied 2 over here. If you differentiate dz with d sigma, you'll get 1. So in terms of differentiation or finding the gradient, this is still differentiable, and you can still do by backprop. Okay.
Yes, sir, but we said that in the middle, right? The sampling is random. Correct? Like in
now it's not. Now see, the random portion is coming from here now. Mu and sigma you're not modifying them anymore. You're taking those two values, adding them. The only difference is that you're multiplying, sigma. You're multiplying sigma with a specific value, say 2. Okay. So in terms of, it is still differentiable. So in terms of backprop, there will be no problem as such. Okay. However, interestingly, the number that we multiplied with sigma will be actually sampled from some other parallel distribution which is a 0-1 normal distribution. But since this does not, this portion is not learnable, we don't need to learn this portion, we can consider this value as a constant. So if we are sampling a constant and adding to these two values, h plus g into this constant, this is still differentiable. There is no problem as such. You can still differentiate and get with respect to h and with respect to g, and the backprop can still continue. But by sampling this constant from a 0-1 normal distribution and multiplying it with your with the standard deviation, you have actually sampled from this distribution indirectly, and that's the beauty of this process.
But sir, why do it at all? I mean, why not just directly pass it?
Directly pass what?
The like, why take the constant from another distribution and multiply it to mu? Like directly
See,
just.
that means you're asking me to directly sample from this
Ah.
distribution, which is defined by h and g.
Correct.
Right?
Yes, sir. Yes, sir.
See, you have to keep in mind any of the steps that you perform in your neural network is differentiable only if there is a direct link between input and output. So there should be a function which performs whatever. So consider there is some weight value, some that weight that converts your h and g to z. There should be some function like this. Only then you can consider this as differentiable. What happens with direct sampling is not a deterministic process. It will consider your distribution and will randomly pick one point from here. Since it's random, there is no direct connection between h and g. I'm not connection, but there is no direct equation between h, g, and z, because you're randomly picking one point from there.
Okay. So okay. So you are saying that this h and g will be two separate vectors, and even if we connect it directly to that, it will behave as a two independent autoencoder decoder portion.
Yes, it's behaving like that. You have two outputs. Yeah.
So to combine that to one, you are creating a linear combination to pass it to
Exactly.
the representation layer.
Yeah.
So, sir, suppose take an example. Suppose there are 5 persons, and we have to find that which are the images which are smiling. So, how we can do means we have to pass all the 5 images. I, Pratik, Chandra.
Which are the images which are smelling? But that is a different task. No, that is a classification task again.
Okay.
This is for this entire operation is happening because I think it's there. No, it's there later. So we'll cover that later. But the point is, once when you have trained your variational autoencoder,
Mm-hmm.
what you will do is that you will simply discard the encoder. You will not use the encoder anymore. Since we have forced the mu and sigma to be close to, we have forced this particular distribution to be close to your standard normal distribution. What we can do is that we can simply now sample from this standard normal distribution any value, pass it to the decoder, and the decoder will produce an image that is from that particular domain. So in your particular case, if you have faces, this variational autoencoder will ensure that any sample that you draw from a normal distribution or a Gaussian distribution and you pass it on to this particular decoder will get mapped to an image of a person. Okay, and some of these persons will be smiling, some of them will not be smiling. Classification is not the task over here, at least
But
specifically.
it will give the probability of Pratik is smiling, probability of Chandramohan is not smiling. Then we will get to know that okay, you are the person.
No, I did not hear. You give the probability where? Probability of smiling where?
Sir, in the encoder.
In the encoder. Acha, you are saying conditional. Acha, sorry. You can actually do conditional VAs
Yes.
where you can mention the class as well. So we will look into that tomorrow.
Okay.
So then, based on the condition, you can basically generate specific class images as well. That is possible.
Okay.
Sir,
Yeah.
sorry, sir, what extent of variation will we get? What I'm trying to say is, that what stops it from just varying the brightness a little bit and contrast a little bit and just calling it as a variation, because that eventually gives us a good output.
See, the point is that we are not explicitly training it for variations. Okay. But what we are doing is that we are showing it a set of images. What it learns to do is combine these set of images and learn from different types of images. I'll just show you an example. I have.
So does it go to the extent of, a non-smiling person making it smiling? To that extent?
It can. Provided you have shown it both images of smiling as well as non-smiling persons. So just look at this latent space. This has been generated using a VAE that was trained on MNIST. And then what I fed this VAE or the decoder was values between, values from this between -1 and 1. And based on those values, just look at the number of, numbers or different strokes at least it has been able to generate. If you train it more with much more variations, which better loss functions, it can even generate much more different types of variants as well within that numbers. So if you can look at the different types of images that it is created of different numbers, different slanting angles and others. So this has been done without explicitly telling it which number it has to produce or what is the angle of that number, how it should look like. Without giving any information, it is able to do all of this. And it's not just simply changing the lighting of that particular image. It is automatically learned. And this is happening because we are forcing all of the images to lie within the same distribution. So if we have forced all the images to lie within the same distribution, that now when you fetch any point within the distribution, the decoder will produce a corresponding output that may match the number from say 4, but it will match the say pattern or say type of writing from say 6 or something like that. So it will combine all of this information and create a new image. Yeah, I think Ritesh is.
Sir, our other class has started, sir. Blockchain.
Yeah, okay, fine. We can continue tomorrow.
Sir, one request.
Thank you, sir.
Yeah.
Hello, Pratik sir, one request, sir. Next semester, sir, we have to choose some of the subjects, and most of us are interested for taking computer vision. So we request you that you should open computer vision for.
It is open for executive.
Okay.
It's in a hybrid slot.
Okay.
Thank you, sir.
Thanks everyone. I will stop the